Okay, guys, welcome to the sixth review preview session for ENGI at 1331. We have decided to move away from the live recording sessions and just be posting YouTube videos. We have found that a lot of you guys just like to watch the YouTube videos, which is cool because that saves me a little bit of time on Sundays. So this video is going to be covering obviously a review of function handles, which you guys have covered in class this week, and we're also going to talk about regression and plotting. So that's a new topic you guys haven't seen yet. But to begin with function handles, this is a basic example of a function handle. I know you guys have seen the syntax before, so you guys have the name of your function and what it is. So you're defining it as x being our independent variable. So x being x as it usually is in just like a normal function of y in x, right? It just acts as our independent variable, y being our dependent variable. And so when you run this, we get two functions right here. Y, it's saying is its dependent variable is x, and this is the function we get. So if I were to say g becomes y at 3, what would happen is we plug this value 3 in for every value of x in this, and it would spit out whatever value that is and store it in g, just like that. And so obviously you see that these functions are just another way to define something just like this. Up to this point, you guys see that it's the exact same thing as writing an out-of-script function. So all we did was define a function called polynomial, and instead of saying y at 3, polynomial at 3, so long as we were to save this function, right? And so 3 would then go into for x would be here as our dependent variable and would spit out a value y would be our output, and it would store in g. These function handles are a lot more useful than that. They're a lot more useful than just being a shorthand way to write out these out-of-script functions. And they're useful in a way that they can be used much more easily for mathematical modeling. So they can be plotted a lot better. They can be used with an integral function. They can be used with an fzero function, and they can be used with an fminbnd function. Those are three functions I'm going to cover today. Another couple pointers I want to give you guys about function handles is that function handles can have multiple inputs, so multiple dependent variables, and they can also be used with vectors or matrices. The size of the variables doesn't matter. So you see how I'm using a dot operator, meaning I'm expecting it to be a vector or matrix, right? So they can be used with vectors or matrices. They can also be used with different variables, so long as these variables are defined every time they're called. And so right here we have a function calculating the magnitude of a vector given its x, y, and z components. So if you guys watched my video on user-defined functions, we did this, but just in a separate script. Here now we're just doing it shorthand. And you can see how these function handles are always one line. And that's again because they're shorthand of these, but you're not going to be able to use these function handles to write out multiple line functions. So for example, in here we could have if x, whatever value we put in for x is greater than 3, we could use some other function y is defined as something else. Else if x is less than 3, so anytime x is less than 3, y could be a completely different function. And so you see how we can't do that with function handles because they're single line, right? They're just quick numerical statements. And I mean, they can also be used with data types other than numerical, so they can be used with string inputs or logical inputs, but in this class we're going to stick mostly to numerical inputs. So you're usually going to be using them for things like defining an equation. Okay, so the next thing I want to talk about is this example I have for you guys. And so this example is four parts. So the first part would be to plot a set of 20 random coefficient second degree polynomials using function handles. Oh, function handle functions. That's not a typo. We'll see what function we're going to use for a function handle in a sec. Part B is to find all x values where a random coefficient polynomial has a y value of 0. So we're basically going to define a random coefficient polynomial every time, but we're going to define it once, and then we're going to say, okay, where does that function have a y value of 0? Part C is to take an integral of a random coefficient polynomial from 0 to 100, And part D is to find the lowest y value of a random coefficient polynomial. And you'll see that all four of these is going to take a different function we haven't necessarily used yet. Well, I mean, in these videos, of course, you guys have used them in class to complete your MAs, right? Or at least the last MA. So part A, plot a set of 20 random coefficient second degree polynomials. So a second degree polynomial has three coefficients, right? So I'm going to go ahead and define A being my first coefficient as randi. We're going to use the randi function again, and I want to define it from -10 to 10. Now that we have our coefficients defined each time, we can now define our function handle, right? So let's say y equals at x being our dependent variable. This is a polynomial, a second degree polynomial. So this is the definition of our function handle y. We want to plot it. And so the function I'm going to use is called fplot. So the way we use that is we say fplot, just like plot, so we have an f in front of it. It asks for f in our x interval. So what that's asking for is what function do you want to plot? Well, we want to plot y, but then we want to plot what interval to find an interval from -100 to 100. Okay, so now -100 to 100. We get the polynomial with random coefficients a, b, and c right here. So now if we want to do this 20 times, all we have to do is say a for loop I equals 1 through 20 and plot this 20 times. We're going to say figure 1 and we're going to say hold on. And that should take care of that. So now if we plot all these, they should all pop up on the same figure. And this figure is just 20 polynomials with 20 different random values of a, b, and c each plotted on the same graph. But we did this in another video. I believe it was the user-defined function video. So it's the exact same thing here. But you can see how we used it shorthand inside of this script. So every time this for loop ran, we say for I equals 1 through 20, so it's going to run 20 times. The first time it ran, we defined a, b, and c to be a random integer. Then we defined y using that a, b, and c. So we defined a polynomial y of in x with those coefficients a, b, and c. So once we get to this definition statement right here, a, b, and c are already constants, are already defined. So we don't have to worry about them being changing every time, right? Every time this for loop runs, a, b, and c are defined as constants before we define the function. And so what we do is we use that function to plot it from -100 to 100 using fplot. So I've changed up part B a little bit. Instead, we're going to find all x values where 2x squared plus 5x minus 23 equals 0. So we're going to find out the x values where y equals 0 for this function. And so what I did here is the same exact thing as last time. I defined my figure window. I said, hold on. And I said, I defined A, I defined B, I defined C, and then I defined my function with those three constants. So I'm going to use fplot again to plot the function y. Let's say on a range from -10 to 10, something simple. Plot it. We see it looks like it crosses 0 a couple times, which we expect for this polynomial. So to see exactly where, let's just plot a horizontal line from negative to x values -10 to 10, horizontal line, so we need both values to be 0. We can see it looks like it's about here and here. Now we could zoom in if we really wanted to, zoom in on that and be able to pick out the point. But to get our program to do it, we can use a function called fzero. The way fzero works is just like fplot, you put in your function, but this time we only put in one y value or one x value instead of a range of x values. And so let's say we put in -10, or we started plotting. We get our plot again. X stores a value of negative 4.8642. See if I can put it. Look, it looks like it's really close to negative 4.862. It's about negative 4.5 at this point. It could be negative 4.8642, which it actually is, since I know how this works. The way fzero works is you put in a function, you put in an arbitrary guess, negative 10. If I were to put in, we get negative 4.8642 for x, which is really close to this one, and we get 2.3642, which is really close to this point right here, which looks like it's almost on the bound. And so the way fzero works is it takes some arbitrary guess and locates the zero closest to that. So say negative 10. Actually, say negative 4. So the way fzero works is it takes this x value, negative 4, goes up onto this function, and then jumps this way a little bit. If it doesn't find a 0, it jumps this way, and jumps this way, and jumps this way, and jumps this way. And you can see how it kind of expands the jump every time. So what it does is it's basically moving outwards from this point, negative 4, which is, say, was our guess, and it moves outwards until it finds the x value where y equals 0. And then it outputs that to whatever variable we stored in. And so you see how I picked negative 10 over here. The closest 0 was this printed out the x value for this 0. If I would have put out negative 4, it would have done the same thing, printed out this x value. But if I were to put out 2, this one's closer, so it picks this one. If I put out 10, this one's closer, so it picks this one. So if we didn't know our bounds of our function, say we didn't know what we were plotting on, we were just plotting it, and we didn't necessarily know our minimum, we didn't know our x value where our minimum would be, how are we supposed to find both zeros? Or what if it's a sinusoidal function and it has tons of zeros? The way to do this is with a for loop. Start at negative 10, so let's start at our bound. We're going to use a small, small, small increment. So what we're going to do is we're going to say, we're going to define a vector, zeros becomes an empty vector, zeros then becomes, and so now what we're doing here is we're using a for loop to vary this guess, I. And so what we're doing is we're starting at negative 10, and we're using the negative 10. And so we're going to get this 0. It's going to store in the first value of zeros. And we're going to move again a little bit by 0.1, use this guess again. But as you can see, as we move closer and closer to this, we're going to keep picking this 0 right here. Keep picking it, keep picking it, keep picking it, keep picking it. But once we get past the midway point, then we start picking this 0. Once we get past the halfway point, we're now closer to this 0 than we were to this 0. So now it'll start picking this point. And so you can see for a sinusoidal function, maybe it was going up, down, up, down, up, down, up, down, up, down. It would, as it moved along, it would get close to 1, 0, pick that one for a little bit. Then when it gets to a point where it's closer to another 0, it would pick that one for a little bit and keep moving. So what happens is we get a big old matrix zeros, a 1 by 201, but with the constant value of negative 4.8642 until we hit the 0 point. So it looks like it changed. It changed about 0.1, negative 10 plus 0.1 times 88. So it changed about in our 87th or in our 88th iteration of our for loop. So part C is to take the integral of the function above from 0 to 100. I changed it a little bit from what we started with, but it's basically the same idea. So we're going to redefine NV. I'm going to redefine A, B, C, Y. But we're going to be careful to make sure we have our dot operators in before x, before our multiplication of x by a and b, and before we square x. And that's because the function I'm about to introduce is a little finicky with matrices if you don't have the correct dot operators in your functions. And so we're going to find a value j as the integral of y. Let me show you guys the syntax. The integral of our function from xmin to xmax. So let's say we want to use the function y from, I believe it was 0 to 100. We run this. Need the value of j to be 6.8937 times 10 to the fifth. That's all we got to do for this example. And so this again is another function we can use with function handles. fplot, another function we can use with function handles. And you can't use these functions with regular functions. So you couldn't use it with an out of script function. It wouldn't work like that. That's another thing function handles are quite useful for. Part D is to find the lowest y value for a random coefficient polynomial. So let's define these again since we're using random coefficients. So we define our figure window, say hold on. We define only one A, 1A, 1C, or 1B, 1C from a random integer from -10 to 10 each. We define our function y. Let's say I want to plot it just to show you guys from, let's say, -10 to 10. And so what we're going to use is a function called fminbnd. So we're going to say little m becomes fminbnd of our function x1 to x2. And so we're going to plot our function, or we're going to use our function y. We're going to say -10 to 10. I see what I did wrong, guys. I forgot my brackets. Should only be one value, meaning that we want to set our range as only one input to our function. As compared to with fminbnd, we have two different x values, and with integral, we also had two different x values of this to kind of give you guys a better depiction of what we're looking at here. So if I only have a positive value on a all the time, it's going to be a upright second degree polynomial, or a parabola, and our m value is going to be 0.3571. It looks like it happens right about here, if we can pinpoint it. It's about right there, and that's about 0.2 right there. We're looking at about 0.3, so it's pretty close. And so what it does is it pulls out the y value at your minimum. All right, guys, so the next section I want to get into is the regression and plotting section using Polyfit. So right here I have just my housekeeping commands. I have a figure to find and hold on. And the reason for that is because we're going to be working a lot with plotting in this section. So I want to make sure that all of my plots stay on the same figure, obviously. So regression is building a function off a series of points. So building an equation off a series of points. And plotting is, well, just plotting, right? And so the way we're going to build this equation is to using the polyfit function. And so what that does is it takes a set of x values and y values and it spits out coefficients depending on if we want an exponential curve, if we want a linear curve, or if we want a power curve. We're going to start with linear regression since it'll be a little easier for you guys to kind of interpret. So we have x values t1 and we have y values v1. And so we're plotting a temperature volume curve, basically. If I run this, I'm going to get this plot right here. And so don't worry about this SK, this marker size, and this 10. That's basically just saying I want black squares and I want the size to be 10. So I just wanted them to be a little more obvious to you guys. And so you can see from this point, or from this plot, that they're points, right? So they're experimental data. And we want to be able to build a curve off of this that fits this data. That's the point of regression. So to do this, we're going to use a function, like I said, called polyfit. We're going to define this as linear coefficients becomes polyfit. We open it up. It asks for x values, y values, and a value n. So I said temperature is going to be our x value. Volume is going to be our y value. The value n is going to be a 1. And the reason for that is because we're looking for a 1-degree polynomial. Not a second degree, not a third degree. We're looking for just a linear line, a 1-degree polynomial. So if I run this, lcoef spits out two numbers, which is what we wanted. And so those two numbers are, the first number is going to be our m, the second number is going to be our b in this equation right here, because we're looking for a linear line. M linear to be L coefs at 1 B linear to become L coefs at 2. And then so we can use our previous knowledge of function handles to define a function in X by using these two coefficients. And so now what I did was I used a function handle to build the equation we want here. And this equation right here will model these points because we use these points in the polyfit function. So now if I use fplot from, or first using the function y that we built, let's call it yl, so we know it's linear. Let's go from 240 to 320, the two x values that we have. 240, 320 being our minimum and our maximum x values. Now if I run this, I'll get a linear line that kind of fits this data. This can also be done by defining yl instead to be ml dot times x, let's call it L, plus BL. And before this, obviously, you'd want to define XL, where XL being, let's say, just a range from our starting value. So we could really do T1 at 1 from 0.1, let's say a very small increment, to 320. Or I'm sorry, T1 at end. So we don't hard code it. It will plot the same exact curve. See, it's just right on top of it, it's a different color. But this line doesn't really fit this data correctly, right? It doesn't fit it exactly. It looks like this kind of goes up. It curves up like an exponential curve, and that's exactly what it is. It's the data would most likely fit an exponential curve, and I pulled it from a separate example for an exponential curve. So now we're going to look at exponential regression, and you're going to see that this kind of regression is almost exactly the same as linear regression, except we have to do a few things when we use polyfit. So we have the same plot this time, except we want to plot an exponential curve this time. We're going to use the same thing. Let's use exponential coefs becomes polyfit of, we're going to use T1, the x values we did last time. But now that we want an exponential regression, we're going to use the log function of our y values, so v1. And of course, we're going to use the first degree polynomial again. We run this, we get two coefficients again, except our function is going to look like y equals b times e to the m times x. That's what our function should look like. For b exponential, we're going to have to use the exponential function of exponential coefs at 2. For m, we're just going to use m exponential. We're going to just use exponential coefs at 1. You guys are going to get a sheet on the test that tells you when to use log or when to use the exponential of something, because power is going to be a little different as well. So now that we've defined our coefficients, we can use another function handle to define it again. So now we're going to use b exponential times the exponential function of m times x, which is just m exponential dot times x. This is just another function handle, but in the definition of our function handle, we defined b exponential and m exponential from polyfit. So now we're developing these coefficients in a little different way, right? And now if I use fplot, now if I run this, we get a curve that looks almost exactly like our data. And like I said, the reason the linear one didn't match is because the curve didn't really fit a linear, or the set of data didn't really fit a linear curve, which was intended. But like on a test or something, you guys will have a problem that says, okay, fit this to a linear line or fit this to a power line. You guys won't have to figure that out. And again, we can do this the same way. We can always say define our y values like we did last time. We can say instead of the function handle and the fplot, we could just say define a range x and then define a vector y from that x and then plot that. But I like the function handles a little better. Okay, so the next and the last regression I want to get into is the power regression. And so we have different x values and different y values this time. These points are going to fit a power curve, as you guys are going to see. So if I plot this, this is my curve. It's almost the same exact thing as last time. We're going to use p coeffs, power standing for power coeffs, to become polyfit. This time we're going to use log 10 of our x values. We're also going to use log 10 of our y values. And of course, we want a first degree. So again, you guys are going to be told when to use log 10 versus logs. You won't have to memorize them. MP, standing for m power, becomes c, or p coeffs at 1. BP becomes p coeffs at, or I'm sorry, 2. But instead of this, we're going to be using 10 to the power of p coeffs at 2. So this is going to be our b coefficient. That's our power curve. So becomes, we're going to use another function handle again, using bp x to the mp. We define our function with coefficients that we got from Polyfit. Then we use that function handle in fplot to plot it. So if I run this, okay. So this should be v2 instead of v1. I just got an error, but just to let you guys know, that should be v2, not v1, obviously. We run it, and we get a power curve that fits our data pretty well. And so this is the whole point of regression. We're going to take some experimental points and fit a curve to these points. And so the reason I tell you guys about this, the reason we're going to be needing to know how to use Polyfit is because we're going to be building things like this. This is a phase diagram. And so what it is we built these curves off of experimental points. And then we said, okay, given this now graph that we have, give me a temperature and a volume. And I want to see with that specific temperature, so say if it's 290 and we have a volume of 4 liters, so our point would be right here, tell me if it's a liquid or a gas. So if it's inside this curve, it's a liquid. If it's outside this curve, it's a gas. And so with our program, we're actually going to be able to do this. And you guys are going to see this a lot next week.